Hello, Professor Simmons here. We're going to do an example of finding the area of a curved surface using the method from the previous video. We will do an example where we know what the answer is. We'll prove that the surface area of a sphere of radius 1 is in fact 4 pi. So to start, we look at the equation defining the unit sphere, and we say that, we need to put that into the form required by our method. We have to rewrite it as z equals some function of x and y. And when we do that kind of rearrangement, we find z is the square root of 1 minus x squared minus y squared in our case. So the square root function becomes our f of x and y. Next, we need to set up the integral and the limits that we're going to use. We want the area of the full sphere, but half of it would be above the xy plane, half of it would be below. The two halves are going to give the same answer, so let's focus on the half that's above the xy plane, as in our method. And in fact, each of the 4 equal parts of the half sphere that's above the xy plane would give the same answer. We're going to focus on the octant of the sphere that has x, y, and z coordinates all positive. And the answer that we get for the surface area of that octant multiplied by 8 will be the full answer for the sphere. Now remember that we do the integral by saying the area of the curved surface is dx dy times the projection angle at each point of the curved surface, and that's integrated over x and y up to appropriate limits. What are the limits here? Well, think about projecting the curving surface down onto the xy plane. Since we're doing the integral in the xy plane, the hemisphere projected down onto the xy plane would look like a disk. And if we're just looking at the part where x and y have values greater than 0, it's in fact just this little quarter of the disk here that we're interested in. And we see we could think of marching along the x-axis from 0 to 1. At every point, y will be constrained to lie within this circular region here. So y can never be larger than the square root of 1 minus x squared. And so that becomes the upper limit of our y integration, while x marches all the way from 0 to 1. So we're integrating between these indicated limits, dx dy secant gamma. The big question is, what is secant gamma? Well, we remember from our method that we find secant gamma by taking derivatives of our function f. And we said our function f here is the square root of 1 minus x squared minus y squared. We need the partial derivative of f with respect to x, and that literally works out to negative x over z. We need the partial derivative of f with respect to y. That becomes, it turns out, negative y over z. By our method, secant gamma is simply the square root of 1 plus the squared partial of f with respect to x plus the squared partial of f with respect to y, and that gives this result here. Now looking at that, we realize that if we replaced 1 by z over z squared, the whole object under the square root would be 1 over z squared, because x squared, y squared, and z squared sum to 1. So secant gamma is simply 1 over z. But 1 over z, we said, is 1 over the square root of 1 minus x squared minus y squared. So we now have a formula for secant gamma in terms of x and y. We can plug it into our integral and find the result. So this has encompassed everything from our surface area integral method that tells us how to set up the problem. On the next slide, I'll walk you through doing the actual integral to come out to the final answer. Now let's do the integral that we've set up. Remembering, we're integrating the area of the whole sphere as 8 times the surface area of the single octant where x, y, and z are all positive, and we established that that is the integral shown here, where we're integrating secant gamma, this square root function, over y and x from these particular limits shown here. And in particular, we'll do the y integral first. While we are doing the y integral, of course, x is simply left constant, which means we could rename 1 minus x squared as just a constant a squared in doing the y integral, which makes things a little bit easier to look at. So we've done that here. Now we see that in doing the y integral, we could use trig substitutions. For example, call y by the name a sine theta, which would make dy equal to a cosine theta d theta. Notice this a cosine theta factor is something that we will be calling a Jacobian in class. Having done this, we realize that the integrand can now be simplified, and we need to remember to rewrite the limits as well if we're going to use the new variable theta. Y equals 0 translates to theta equals 0. Y equals a translates to theta equals pi over 2. So our integral takes this new form. That's an easy integral to do. It works out simply to be pi over 2. Now we can do the x integral, which is equally straightforward, and the final answer is 4 pi. Really, the important things here are, first, that the method overall gave us the familiar answer for the unit sphere. Second, we see that secant gamma is really not that hard to deal with. Third, a reminder of trig tricks. And finally, a reminder that when you change variables in doing an integral, you have to be careful to change not only the integrand, but correctly change the differential and the limits. We'll certainly be expecting you to remember this all through the course as you encounter a variety of cases where changing coordinates is important. That's all.